my name is Ishan Patel, and I'll be showing our project about parallel image processing using OpenCV. So this is our table of content. First, we're going to talk about what is OpenCV. Then we're going to talk about how multiprocessing already exists in image processing utilizing OpenCV. Then after that, we're going to compare OpenCVs versus our own method that we decided to use. We're going to do a quick runtime analysis of basically what we're expecting for the running. Then we have our live demo, testing results, and conclusion. So, OpenCV is basically a open source free library often used for Python for image processing, computer vision, and machine learning tasks. It's all written in C++. However, we utilize our code to be able to access it on a C++ level. So, this is the application of OpenCV in this project. Specifically, we're going to be using it to focus on image processing and using it to apply kernels on images. And the kernels that we'll be using are only going to be limited to the median, the Laplacian, and the Gaussian filter. So to understand how image processing work, we're going to use this image, which is represented in by M by N image full of data, numerical data. This represents how the image is being stored, and this is what our code would be able to read. Here is the kernel. Kernel is basically how we're altering the image and applying it, and this is the expected output. So basically, we take this image, a 3x3, a small section of the image, and have it multiplied in a matrix term with this filter. So here we have 0. We have -1. So -1 times 134 equals -134. And we do this for each one. So as we see, 119 times -1 is -19. -1 here times 83 is -83. -1 times 80 is -80. And then 5 times 99 is 495. Now, once we have all these numbers multiplied, we would then add them all up together. And then that would become 79. Now, this only affects the center pixel or the kernel. So in the next image that we will have, it would only apply it to that one single pixel. So we're doing basically 9 multiplications in a 3x3. This in a 3x3. And this project is only limited to using odd number kernels because that is how OpenCV works, and this is how they utilize it. So how does multiprocessing already exist in OpenCV? So as we were researching more into OpenCV and how they do multi-thread processing, they simply take the input image and then they divide it into sections, horizontal sections. So here we're assuming that OpenCV takes the image of an apple and then decides to use 3 threads. And if it wants to use 3 threads, it needs to equally cut off the image horizontally into 3 sections. So we have thread 1 being used here, thread 2 being used here, and thread 3 being used here. Therefore, each thread will then apply a kernel, basically a median filter, a Laplacian filter, or a Gaussian filter. They would then each apply these filters on their own section simultaneously. And that is how multiprocessing already exists in OpenCV. So what is our approach to OpenCV? So our approach is to take an apple and then we divide it into 4 sections. Then, in those 4 sections, we assign each section to a thread. So in this case, if we divide the image into 4 sections like this, that means we'll have 4 threads, each actively computing the image. However, if we want to have more threads, we do it by the 4 to the power of n, where n representing the levels. So at n equals 0, the level is basically No, only a single thread, and this is the image we're processing. At n equals 1, we're dividing the image into 4 sections, which would then result us to having 4 threads. Now, if we were to say at 4 to the power of 2, which is when n equals 2, we're taking it to the second level, where we then divide each of these boxes into 4 more boxes. So 4 to the power of 2, when n equals 2, is 16. That means we'll have 16 threads, each processing each of these boxes or segments of the image. And that is how we're trying to process our image compared to OpenCV's traditional method. So here's a side-by-side comparison. So the splitting method is basically OpenCV's horizontal strips. Our method is to use recursive 4 to the power of n squares, which means that n being our recursive level. Flexibility is that OpenCV is only row-wise. That means they could only have X amount of rows for the length of the image. However, ours is dynamic in the sense that we're not limited to the rows, but rather the entire image. The scalability for OpenCV is linear. This means that OpenCV can use 1 thread, 2 threads, 3 threads, 4 threads, or 5 threads. It has a scalability of n. Our scalability is exponential, which means it's 4 to the power of n. That means we can only use 1 thread, 4 threads, 16 threads, 64 threads. And those are the different scalability of our application. So the time complexity for both OpenCV method and our method is basically the same. P represents the total amount of pixels in the whole entire image. So we have a 20 by 20 image, so that means we have 400 pixels in total. R represents the total amount, the number of threads we're using. Basically, if we have 400 pixels and we are using 4 threads, that means each thread will then be processing 100 pixels. Then K represents the kernel, or basically the kernel size. So in the example we showed earlier, that's a 3 by 3 kernel. So if we're using a 3 by 3 kernel, K would be 3, which would then become 9. So this is basically time complexity, which shows that OpenCV's and our method are basically the same. However, that doesn't always mean that they're always going to have the same amount of runtime. So what are we testing? So we're testing our method to OpenCV with CPU usage, memory usage, and then actual processing time. CPU usage basically tell us how much of the processor are we using when we're processing the image. Memory usage is basically how much memory are we using, in the sense of that we're not constantly going all the way to the disk to retrieve data. Instead, we're using locally cached data. Actual processing time is basically how fast the image is being filtered and how fast it is completed as a whole. So those are the units of measurements that we'll be doing for our demo and that we will be showing. So here's the live demo. So we'll go here to our command. This is our main C++ processing. Here we have our libraries, which is basically OpenCV, IOStream, thread, and vectors. This code is basically used to say how simple our code is, in the sense of we're only going to be able to add images to our project file, which is basically called image JPEG. And if it loads, yes. So this is the image we'll be using for our example. This is the command. So the top here is basically our compile code. This is how we compile our code to compile our code. The reason we compile this is because we need this to basically connect our code to the OpenCV library that we have installed. So we've installed our OpenCV on our base drive to a dev folder, which then contains all of the OpenCV notes and resources. Then once we compile it, we will then execute it using this main function. Now going back to the code, this is our code. So here we have load the image from a file path. Basically, we're only limiting, basically, this is saying like, hey, this is the image we're doing, and then this is what it is. This is basically function to apply median filter to an image. So here we're taking the image, and then we're taking kernel size. Kernel size is the main thing because that tells us how big of a filter it is. Median filters basically takes the whole kernel and then averages all the values and then just places it in the middle. And then once it applies that image, it will then return filtered image. This is the Laplacian filter, same thing as median except different on purpose. This is the Gaussian filter. Gaussian filter has another input requirement, which is sigma x, which is used for the Gaussian blur. And as such, they all return a filtered image. This is what we're using to display our image for testing purpose and basic understanding of this is the image and then this is how it's altered. So before and after. This is OpenCV. This is the OpenCV code that we're using to basically emulate how it is being used. So for this code, we have two sections, which is mode 1. Mode 1 basically represents OpenCV's own method. This basically takes the image, the vector, and the number of threads. And then based off of the number of threads, we then divide that image into that many sections. And we do this by taking the height of the image, and then we divide it by the number of threads. And then that creates how tall each segments are going to be. And then this basically loops for the number of threads to assign each a section of the image using the OpenCV method. This is our method 2, which basically takes in our half width and then half height. So if n equals 1, we're just basically saying that we're dividing the image into 4 sections. We will basically divide it into 4 sections. And then we will then, return here. And this is our return function, basically saying that, hey, we're done. This is all we're doing. And this is our recursive call. So basically recursively split the image into 4 sections. The function to apply the filter to the image. So this is the actual application of, hey, this is a user input, and then we're then deciding what filter we're applying. So in this case, we're using a switch case where we're taking the user's input 1, 2, or 3, and then applying the filter that they desire. And then obviously we copy the filter, the output, and then we print it out. And this is our main image, which our main function. This is basically taking the mat image load, which is basically saying load image JPEG, this image, which is seen right here, our image JPEG. Going back to main, we then display the image saying this is the original image. After that it's being run, then we go back here and then we ask the user what mode they want to use. They say OpenCV or the unique 4x(n) splitting method. This is basically asking us how we're going to split our code. Then we're going to ask the user which filter they want to apply. OpenCV has a lot of filters and a lot of customization they can do, but as a demo, we're only showing 3 cases, just in this case. And then we're going to ask for kernel size. Kernel size must always be odd. And then if we are doing the Gaussian filter, we also require sigma x to say for the Gaussian filter. Then at the end, we then ask how many threads they want. And then this prepares the output image, which is just taking the image right here. And then we set OpenCV num threads to 1, basically saying that OpenCV can only use 1 thread at a time. This is a problem we had earlier where OpenCV would innately always apply multiple threads when doing their filtering. So if we do Gaussian filtering and we said only one thread, it would, in the library in the back end, it would automatically apply multi-threading processing. That's not the case for thread 2 because of how we set it up. And then this is handling the splitting mode for mode 1, which is the OpenCV method, and this handles the splitting for mode 2. And then if we're doing mode 2, we also ask for how many recursion level we're doing. This basically prepares for multi-threading. This creates the threads to process each region, which is then based off of how many levels we're doing or how many horizontal sections we're doing. Then as the threads are being processed, we wait for all threads to finish, and then they automatically join back together. And then it will display the filtered image, which is the image output, and then we return 0. So to run this code, we will go to our command text, and then we say, this is the code we want to copy. This is what we paste, and we click enter. This would compile the code into our main execution. Basically, our executable file. Okay, this means that it is ready. And now we will execute the file by doing this, main.ex. So the code, as obvious, they show us our image first, which is this image. And then to continue, we have to exit out, and then it'll ask us which mode we want to do. For the sake of it, let's do mode 2. And then for this part, it's going to ask us which filter we want to apply. So we're doing the Gaussian filter. So Gaussian filter has a hard time seeing the difference if we do it at a low setting. So for this, we're just going to do a kernel size of 5. We're going to do a sigma x of 5. And then we're going to do 3 levels of recursion. So that means we're going to do 56 threads for processing this one image. And then this is the image that is outputted to us. So this is basically the gist of how the code runs. Now, as we said before in our presentation, we're also doing analysis of understanding what method is the best method between them all. So we created this code, which is basically to test both methods with varying images. So here we have our easy images and then hard images. And then we have our report saying new method easy, new method hard, OpenCV easy, OpenCV hard. So the difference between easy images and hard images is that easy images are simple images that doesn't have much change in color, it's simple, and it's easy to process. So as we see here, this is a simple image. Simple images basically means that there's not much change between pixels. So if we were to divide this images into sections, it'll be divided like this and then like this. Because there's so much white space, the OpenCV would just easily go through the code very fast and very easy. And these are just all simple photos of fruits I saw. I was like, yeah, let's do fruits. So these are easy images. And of course, these are images outputted. Basically, this is what it is being applied to. So this is the hard images. Images that are hard to process. These images has a lot more edges, a lot more details, and a lot higher resolution. Higher resolution means higher amount of pixels, which means that there's a lot more for the code to actually process. And we have 10 of these each. And then, of course, we have hard applied. So that's the after, and this is the after part. And these are the notes basically saying this is how we compile our code and this is how we execute our code. And then these are the reports that are outputted by our code. So these basically say what is our filter set it at. So here it's a mode of easy. It's using the new method, using the easy images and applying the Gaussian filter at a kernel size 5 with a sigma 5 and a recursion level of 3. New method means that this is applying 56 threads on that image. And we see the same thing here. We see report for new method hard, new method easy, and then new method, OpenCV hard. So this basically describes the filter, basically gives the user a brief understanding about what we're testing or what was just applied. These are images results. So we take the time, we take the measurements that we've done. So in this case, our measurements for this code is time, memory, and then CPU usage. We would measure each instance 10 times because that's how many images we have, and then we also average it all together at the end. This is basically saying that this is the difference between our code and OpenCV method of multi-thread processing. And this is our test function, basically how we do it. It's the same concept, same base code from our original code used for the demo to say like, hey, this is it, except we applied multiple new things such as Windows, PS API, Chrono, file system to just include more for measurement purposes. As we see here, this is most of the same code that we've used in our previous code. So this basically says this gets memory usage in kilobytes. This gets a rough CPU estimate. Because this is in C++, it's kind of hard, but this is how we get an accurate reading of the CPU usage. This is our main. This is configuration, which is hard-coded. It won't ask you for the code, except you'll just simply put it in right here. So we can set it to hard. We can set the mode to OpenCV original method. We're doing Gaussian, we'll say kernel size 11, sigma 5, number of threads 64, and then recursion level. And then we basically set out our output folder and report folder. So this is our input folder, this is the output folder. So it says folder plus applied, so we're doing hard. So we'd create a new folder or replace a folder and call it hard applied. And then this is basically determining which method we're using and adding it to the name of the folder. This whole section is just the creation of the folder. If folder does not exist, we just create it. And then we open the report file, and then we write all the information in the report file. So this is basically the header saying what is our filter setting. This is our image results, which is total time, total memory usage, total CPU, and then how many threads we're using, and then this is where we're actually running the code. So as it's writing the report, it would also do the image processing per the instructions. So this is all just the code of CPU usage, memory usage, and then filter image usage. And then this is just average metrics. This is just total time, total mem, total CPU that we keep track of. And we just divide it by count. And this is our report.close. So this is saying that our report is done. So this is basically our testing code. So we're going to run it. So we'll save all. And this is hard-coded at mode 1. And it's set to hard. So we will run this, compile it since we just changed it. This would basically compile it. So then we're using hard and mode 1, which would be new method hard. So this is this right here. So if we were to run it, once it's finished compiling, we would then execute it using this command right here. So it takes a bit for it to actually process the whole thing, but yes. So here it shows that report hard is finished, and this is the whole kernel size. As we see, we changed the kernels and the recursion level. Oh, yeah. So yeah, this is basically the application of our code right here. Average metrics, everything's here. And that is it for our demo. So we will go back. To our results. So these are the results we've gotten from our code. So OpenCV using the easy method compared to the new method. OpenCV took a lot longer and used a lot more CPU and about the same amount of memory, which means that in terms of memory usage, it's basically the same. In the hard images, the OpenCV does a lot better and does relatively the same amount of memory and CPU usage. And we can see how the times. So from the results, we can basically draw to a conclusion that our method excels much better in in processing simple images like strawberries or simple images without much details, while OpenCV method is much better and excels at processing images with complexity than our new method. But as we see that the average time is almost the same, well, for the easy images, our method is much better. The reason why we believe that this is the case is because of how the images are sectioned. Some of the images are just total white space, which for our image excels at computing, which would just be 0 times 0 times 0. Not much change. While OpenCV method is just a lot more complex since they have to go through the whole strips and then they may face a lot of complexity. So yes, this is the end of our presentation and I hope you guys enjoy it. Thank you so much and have a great day.